For 70 years, we've been living inside a lie. The Milky Way isn't 100,000 light-years wide. It's twice that size, maybe even larger. Every classroom diagram, every scientific chart, every trusted textbook. All wrong. New technology has blown open the gates of our galaxy, revealing a structure far bigger, stranger, and more powerful than we ever imagined. This changes everything: how we map the universe, when Andromeda will collide with us, and what the odds are that we're truly alone. If you're ready for the moment astronomy rewrote itself, hit like, subscribe, and hold on. We begin with the biggest correction in modern science. Every poster in every classroom, every documentary animation, every Wikipedia diagram you trusted, they all show a galaxy half the actual size. Scientists have known something was off for years, but the data came in fragments, hints, anomalies that did not fit the models, stars moving too fast at the edges, satellite galaxies orbiting too far out, mass calculations that never balanced. Then the measurements started pouring in: Gaia spacecraft data, James Webb observations, radio telescope surveys mapping hydrogen clouds at the fringes. Each new instrument revealed the same shocking pattern. The Milky Way extends far beyond where we thought it ended. The problem is not that astronomers were careless. The problem is we have been trying to measure our galaxy from inside it. Imagine standing in the middle of New York City and trying to draw its boundaries. You cannot see the edges. You cannot step outside for perspective. You are surrounded by buildings, lights, noise. That is us, floating in one spiral arm, 26,000 light-years from the center, drowning in stars and dust. For decades, scientists used a simple method. They looked at the brightest stars they could see in every direction. Where the stars thinned out, they drew a line. That became the edge. 100,000 light-years, case closed, except it was never that simple. The galaxy does not have a sharp edge like a dinner plate. It fades gradually. Stars scatter outward in thin streams and clouds. Dark matter, invisible and massive, extends even farther. The old measurements only tracked the bright parts, the obvious parts. They missed the enormous halo of material wrapping around everything. Here is what changed everything. Scientists started tracking stellar streams. These are rivers of stars torn from smaller galaxies that the Milky Way devoured millions of years ago. The streams orbit through space like cosmic fossils, and their paths reveal the true gravitational pull of our galaxy. When researchers mapped these streams, they found them circling far beyond the supposed edge. 200,000 light-years, maybe more. The Milky Way is a giant, and we have been measuring a shadow. This discovery does not just change numbers in a textbook. It rewrites how we understand galactic structure. It shifts when Andromeda will collide with us. It doubles the volume of space we need to search for life. Every calculation built on the old size now crumbles. But the most disturbing part? If we got our own galaxy this wrong, what else have we miscalculated? How many other galaxies are twice as large as we think? Picture this. You are blindfolded, standing somewhere in the Sahara Desert. Your job is to measure the entire desert. You cannot remove the blindfold. You cannot use GPS. You can only feel the sand beneath your feet and listen to the wind. How accurately could you map it? That is what astronomers face, measuring the Milky Way. We sit on a rock orbiting an average star in an outer spiral arm. Dust clouds block our view in almost every direction. The galactic center is hidden behind thick walls of gas and debris. We see maybe 10% of the galaxy with optical telescopes. The rest hides in infrared, radio waves, and darkness. For comparison, measuring Andromeda is easy. It sits 2.5 million light-years away. We see the whole thing at once, edge to edge, top to bottom. We can photograph it, map its spiral arms, count its star clusters. Measuring our own galaxy is like trying to photograph your face without a mirror while standing inside a fog bank. Early astronomers had no choice. They measured what they could see. They tracked Cepheid variable stars, which pulse at predictable rates. They calculated distances to globular clusters, ancient balls of stars orbiting the galactic core. They built a map piece by piece, like assembling a puzzle blindfolded. The breakthrough came when scientists realized they could use motion instead of light. Everything in the galaxy orbits the center. Stars, gas clouds, entire star clusters. They move at specific speeds based on the mass pulling them. Measure the speed, calculate the mass, and you can estimate the size. But here is where it gets strange. The speeds did not match. Stars at the galaxy's edge moved way too fast. According to the visible mass, they should fly off into space. Something invisible was holding them in orbit. Dark matter, an enormous halo of it, wrapping around the galaxy like a gravitational cocoon. This is where the old measurements failed. They only counted what they could see. Visible stars, glowing gas, bright nebulae. They ignored the invisible mass, the dark scaffolding holding everything together. That was the mistake. Modern telescopes changed the game. Gaia spacecraft tracks the precise movement of over 1 billion stars. Radio telescopes map hydrogen gas extending into the outer halo. Infrared instruments see through dust clouds that block visible light. Each technology reveals a different layer of the galaxy. Researchers also started using satellite galaxies as test masses. The Milky Way has dozens of smaller galaxies orbiting it. The Large Magellanic Cloud, the Small Magellanic Cloud, Sagittarius Dwarf. These galaxies orbit based on our total mass, visible and invisible combined. Track their paths and you map the true gravitational field. When scientists combined all this data, the answer shocked them. The Milky Way is not the medium-sized spiral we imagined. It is a heavyweight, a galactic giant, double the width, triple the mass. And if measuring from inside was this hard, what happens when we try to measure farther out? Stellar streams sound exotic, but they are actually galactic crime scenes, evidence of violence frozen in time. Millions of years ago, small galaxies wandered too close to the Milky Way. Our gravity grabbed them, pulled them apart, stretched them like taffy. Their stars did not vanish. They scattered into long rivers of light, circling our galaxy in thin streams. Some of these streams are wider than Earth's entire orbit around the Sunday. Others contain thousands of stars moving in perfect formation. We never paid attention to them before. They seemed like background noise, faint, distant, irrelevant. But they are the most honest rulers we have for measuring the galaxy. Here is why they matter. Stellar streams follow orbital paths determined by gravity. Every star in the stream moves based on the total mass pulling on it. Measure the stream's path and you measure the gravitational field. No guesswork, no assumptions, pure physics. The Sagittarius stream is the most famous. It wraps around the entire Milky Way multiple times, like ribbon on a present. Scientists traced this stream across the sky and realized it extended far beyond the old galactic boundary. The stream keeps going and going, which means the Milky Way's gravity keeps going too. Then came the GD1 stream, a thin river of stars in the outer halo. Researchers mapped its curve and found something impossible. The stream bent in ways that required far more mass than the visible galaxy contained. Either physics was broken or we were missing something massive. Dark matter, always dark matter. The streams revealed it like invisible ink under ultraviolet light. The gravitational pull shaping these stellar rivers came from material we cannot see, material extending twice as far as the visible stars. But what comes next is even stranger. Scientists found streams orbiting at distances we thought were intergalactic space, empty voids between galaxies, except they were not empty. These streams proved the Milky Way's influence reaches farther than anyone imagined. Our galaxy does not stop at the visible edge. Keeps pulling, keeps claiming territory, keeps exerting control. The orphan stream is particularly haunting. It orbits so far out that for years scientists debated whether it even belonged to the Milky Way or some other galaxy. New measurements confirmed it. The stream is ours, which means the Milky Way extends at least that far. Each new stream discovery added kilometers to the galactic radius. 5,000 light-years here, 10,000 there. The numbers climbed. 120,000 light-years. 150,000. 180,000. Stellar streams gave astronomers something they desperately needed: ground truth. You can debate where the edge of the visible disk sits. You can argue about where darkness becomes intergalactic space. But you cannot argue with a stream of stars orbiting information. Their path is the truth, and the truth kept pushing the boundary outward, farther than comfortable, farther than explainable with old models. 200,000 light-years. The stream said so. The math said so. The observations said so. The question was no longer how big the Milky Way is. The question became how we missed it for so long. You are staring at the Milky Way right now, or you think you are. What you actually see is the skeleton, the bones, the bright parts. 90% of the galaxy is invisible. Dark matter is not a theory anymore. It is confirmed, measured, mapped. We cannot see it directly, but we see its effects everywhere. Stars orbit too fast. Galaxies spin without flying apart. Light from distant objects bends around invisible mass. The evidence is overwhelming. In the Milky Way, dark matter does not just add extra weight. It builds the structure. Imagine a skyscraper where you can only see the windows, not the steel frame holding them up. That is our galaxy. The dark matter outweighs visible matter by a ratio of 10 to 1. For every star you see, there is 10 times more invisible mass nearby. This material forms a massive halo around the galaxy. Spherical, diffuse, stretching far beyond the visible disk. The old measurements ignored this halo. They focused on the bright spiral arms, the glowing core, the obvious features. The galaxy appeared to be 100,000 light-years across because that is where the visible stars thinned out. But dark matter keeps going. It extends twice as far, maybe more. Think of it like an iceberg. You see the tip above water. That is the visible galaxy. Below the surface, hidden from sight, sits a mountain of ice 10 times larger. That is the dark matter halo. The true size includes both. Researchers mapped this halo using gravitational lensing. When light from a distant galaxy passes near the Milky Way, our dark matter bends it slightly. Measure the bending. Calculate the mass. The results were shocking. Our dark matter halo extends out to nearly 400,000 light-years when you count the faint outer regions. But here is the twist. Scientists debate where to draw the line. When does the Milky Way end and intergalactic space begin? Is it where the dark matter density drops to half, a quarter, a tenth? There is no official edge, just a gradual fading into nothing. For practical purposes, astronomers use a measurement called the virial radius. This marks the point where material is gravitationally bound to the galaxy. Inside this radius, everything orbits together. Outside, space is truly empty. For the Milky Way, the virial radius sits around 200,000 to 250,000 light-years. Double the old estimate. All because of invisible mass. This changes how we think about galactic structure. Galaxies are not islands of stars floating in empty space. They are enormous halos of dark matter with stars sprinkled through the center. The visible part is decoration. The invisible part is substance. And if our galaxy has this much hidden mass, every other galaxy does too. The universe just got a lot heavier. The Milky Way is not alone. Dozens of smaller galaxies orbit around us like moons around a planet. We call them satellite galaxies, and they just rewrote our cosmic address. The Large Magellanic Cloud is the biggest. Visible from the southern hemisphere as a cloudy smudge, it contains 30 billion stars. The Small Magellanic Cloud sits nearby with 7 billion more. Then come the dwarf galaxies. Sagittarius Dwarf, Draco Dwarf, Ursa Minor Dwarf. Each one a miniature galaxy with its own stars, its own history, its own orbit. For years, scientists treated these satellites as neighbors, separate objects passing by. But new measurements revealed the truth. They are not passing by. They are bound to us, trapped, orbiting within the Milky Way's gravitational sphere of influence. This discovery changed everything. When you measure how fast a satellite orbits, you can calculate the mass holding it in place. More mass means tighter orbits. Less mass means objects drift away. The satellite galaxies orbit at specific distances and speeds that reveal our total gravitational pull. The Large Magellanic Cloud sits 160,000 light-years away. It orbits the Milky Way once every 1.5 billion years. For it to stay in that orbit at that distance, our galaxy must be massive. Far more massive than the old estimates suggested. Researchers tracked dozens of satellites and found the same pattern. They all orbit farther out than expected. They all move faster than predicted. The only explanation: the Milky Way is bigger and heavier than we realized. But the real breakthrough came from tidal streams. When a satellite galaxy orbits too close, the Milky Way rips it apart. Stars get pulled away in long trails. The Sagittarius Dwarf is currently being destroyed this way. Its stars stretch across the sky in a stream wrapping around the entire galaxy. These tidal tails act as test masses. They show where the gravitational field is strongest, where it weakens, where the boundary sits. Map enough tidal streams and you map the edge of the galaxy. What scientists found shocked them. The streams extended far beyond the supposed galactic edge. Some reached out past 150,000 light-years. Others hit 200,000. A few hints suggested material even farther out. The satellites were screaming the truth. The Milky Way is huge. This had immediate implications. If our galaxy is this large, the local group of galaxies needed redrawing. The space between us and Andromeda is smaller than we thought. The gravitational influence of each galaxy reaches farther. Collisions happen sooner. Mergers start earlier. Every satellite galaxy became a data point. Every orbit a measurement tool. Together, they painted a picture of a galactic giant. Not the medium spiral we imagined. And here is the haunting part. Some satellites orbit so far out, we are still discovering them. Every few years, astronomers find another dwarf galaxy hiding in the data. Each new discovery extends our boundary a little farther. How many more are out there? How much bigger does the Milky Way actually get? 200,000 light-years. The number is so big it stops meaning anything. Your brain cannot process it, cannot visualize it, cannot hold it. Let me make it worse. Light travels at 186,000 miles per second. In 1 year, that light crosses about 6 trillion miles. Multiply that by 200,000. The Milky Way is approximately 1.2 billion trillion miles across. Still meaningless. Let me try another way. If you could travel at the speed of light, the absolute speed limit of the universe, it would take you 200,000 years to cross the galaxy. When the light leaving one edge finally reaches the other side, humans have evolved from primitive hunter-gatherers into spacefaring civilization and collapsed and evolved again multiple times. Put it another way, if the Earth was the size of a grain of sand, the Milky Way would stretch farther than the distance from Earth to Saturn. Actually farther. Much farther. Or try this. The light you see from the far edge of the galaxy left before modern humans existed. Before Neanderthals. Before Homo erectus. That light has been traveling since our ancestors were still living in trees. The scale breaks human intuition. We evolve to understand distances we can walk. Miles. Maybe hundreds of miles. Our brains never developed the wiring to comprehend billions of trillions of anything. But here is where it gets personal. That incomprehensible size matters to you. Right now. Today. Double the galaxy's size means double the volume of space. Volume increases with the cube of radius. If the galaxy is twice as wide, it is 8 times bigger in total volume. 8 times more space. 8 times more stars. 8 times more planets. The old estimate said 200 billion stars. The new estimate? Closer to 400 billion. Maybe more. Every single one of those stars could have planets. Every planet could have moons. Every moon could have subsurface oceans. The number of potential homes for life just doubled. Think about what that means. If life is rare, 1 in a billion star systems, we just added 200 billion more chances. If intelligent life exists somewhere out there, we doubled the probability of finding it. Or them finding us. But the size also changes our survival timeline. Andromeda Galaxy is heading toward us at 70 miles per second. When galaxies collide, they do not crash like cars. They merge. Stars pass between each other. Very few actually hit, but the gravitational chaos reshapes everything. Scientists previously calculated the Andromeda collision would begin in 4.5 billion years. A bigger Milky Way means a bigger gravitational reach. The galaxies will start affecting each other sooner. Maybe 4 billion years, maybe less. Your descendants, if humanity survives that long, will watch the night sky transform. Andromeda will grow larger, brighter, eventually filling half the visible sky. Then the galaxies will dance around each other, spirals intertwining, before finally settling into one massive elliptical galaxy. 200,000 light-years is not just a number. It is your future, your past. The stage where every human story ever told took place in one tiny corner. And we just realized the stage is twice as big as we thought. Andromeda is coming. This is not a theory. This is confirmed fact. Our neighboring galaxy is racing toward us at 70 miles per second. The collision is inevitable. For decades, scientists calculated the impact would happen in approximately 4.5 billion years. Mark your calendars. Except those calculations assume the old galactic sizes. Smaller Milky Way, smaller gravitational reach, more space between us and Andromeda. A bigger Milky Way changes the timeline. Gravity reaches farther. The galaxies will start pulling on each other sooner than predicted. Their massive dark matter halos will interact first, stretching hundreds of thousands of light-years outward. When those halos touch, the collision begins. Think of two people walking toward each other. If they are both larger than you thought, they bump into each other sooner. Same principle. Galactic scale. New models suggest the interaction could begin in under 4 billion years. Maybe 3.5 billion. The exact timeline depends on precise measurements we are still collecting. But the trend is clear. Bigger galaxies mean earlier contact. Here is what happens during a galactic collision. First, the outer halos start merging. Dark matter interpenetrating. This phase is invisible but gravitationally intense. Stars feel the pull from both galactic centers. Orbits destabilize. Some stars get flung into intergalactic space. Others plunge toward the cause. Then the visible disks collide. Not a crash. More like two clouds passing through each other. Stars are so far apart that direct impacts are incredibly rare. You could fit millions of Earths between neighboring stars. But the gravitational chaos is real. Star formation explodes. Gas clouds compress. New stars ignite across both galaxies. The Milky Way and Andromeda will orbit each other multiple times. Dancing. Spiraling. Each pass strips away more material. Tidal forces shred the spiral arms. Stellar streams scatter in every direction. The once elegant structures become warped, distorted, unrecognizable. Eventually, maybe 1 billion years after first contact, the galaxies merge completely. The result is a massive elliptical galaxy. No more spiral arms. No more organized disk. Just a blob of 4 trillion stars orbiting in random directions. Astronomers already named this future galaxy Milkomeda. Cute name for the death of 2 ancient spirals. But here is the critical question. Will Earth survive? Will the Sun survive? Will humanity be around to see it? Good news first. The Sun will likely survive the merger. It sits far enough from the galactic center that it will probably avoid the most violent regions. Earth might get flung into a different orbit, or ejected entirely into intergalactic space, or stay roughly where it is. The odds favor survival. Bad news? The Sun will be long dead by then. Our star has about 5 billion years of fuel left. The Andromeda collision happens before the Sun dies. But barely, we might get a front row seat to the early stages. A bigger Milky Way moved up that timeline. The show starts sooner. And here is the part nobody talks about. What if Andromeda is also bigger than we measured? their estimates could be wrong too. If both galaxies are larger, the collision happens even sooner. The gravitational chaos becomes more intense. The final merged galaxy becomes even more massive. We are already seeing the early signs. Andromeda's halo extends toward us. Our halo reaches toward them. The halos might already be touching. The collision might have already begun, slowly, invisibly, in the dark matter enveloping both galaxies. For billion years sounds like forever, but on cosmic timescales it is tomorrow. And tomorrow just got a little closer. Mass. Everything comes down to mass. The Milky Way just gained weight. A lot of weight. Trillions upon trillions of solar masses appeared in the data. The old estimate said our galaxy contained about 1.5 trillion times the Sun's mass. Most of that was dark matter. The new measurements? 4 trillion solar masses. Maybe more. We tripled the mass estimate in less than a decade. Here is what a solar mass means. Our Sun weighs about 2 billion kilograms. A number so large it becomes abstract. One solar mass. For comparison, Earth weighs 300,000 times less than the Sunday. Jupiter weighs 1,000 times less. Everything in our solar system except the Sun adds up to barely 1% of one solar mass. Now multiply the Sun's mass by 4 trillion. That is the Milky Way, a gravitational giant. Where did all this extra mass come from? Did the galaxy suddenly gain weight? Did material appear from nothing? Obviously not. It was always there. We just could not measure it correctly. Most of the extra mass is dark matter. Invisible. Undetectable. Except through gravity. The old measurements focused on visible stars and gas. They estimated dark matter indirectly, using galactic rotation curves. Stars orbit the center at speeds determined by mass. Measure the speeds. Calculate the mass. But those measurements only sampled the inner galaxy, the region where stars are common and observations are easy. Nobody accurately measured the outer halo, where dark matter dominates. That was the mistake. New techniques changed everything. Satellite galaxy orbits provided direct mass measurements at huge distances. Stellar streams mapped the gravitational field in the outer regions. Computer simulations compared our galaxy to thousands of virtual galaxies with known masses. All the methods agreed. 4 trillion solar masses. The Milky Way is a heavyweight. This has enormous implications. More mass means stronger gravity. Stronger gravity means we can hold more satellite galaxies in orbit. We can strip stars from passing neighbors more easily. We dominate the local group more completely. Andromeda was always considered the bigger sibling, the Alpha Galaxy, but new measurements suggest we might be equals, or maybe even larger. The Milky Way and Andromeda weigh roughly the same. 4 trillion solar masses each. 2 galactic superpowers on a collision course. More mass also changes how we formed. Galaxies grow by eating smaller galaxies. The bigger you are, the more you have consumed. A 4 trillion solar mass galaxy has a bloody history. We devoured hundreds of dwarf galaxies. Maybe thousands. Every satellite stream in the halo is evidence of a meal. A galaxy that got too close and paid the price. The Sagittarius dwarf is being eaten right now. Torn apart. Digested. Its stars scattered across the Milky Way disk. In a few 100 million years, no trace of it will remain except ghosts in the data. This is how galaxies grow. cannibalism, galactic empire building. But here is the terrifying part. If we are 4 trillion solar masses, and most of that is dark matter, we live in a galaxy made mostly of invisible material. 90% of everything around us is something we cannot see, cannot touch, cannot directly detect. You think you know where you live. You think you understand your cosmic neighborhood. You are wrong. You are swimming in an ocean of dark matter, and you cannot feel the water. 4 trillion solar masses of mostly invisible material. That is home. That is the Milky Way. And we just realized how enormous it really is. The galaxy does not end where the stars stop. It keeps going, and going far beyond anything visible, into the realm of pure dark matter. Scientists call it the dark matter halo, a massive spherical cloud of invisible particles surrounding the entire visible galaxy. This halo is not a minor feature. It is the dominant structure, the foundation, the cage holding everything together. Conservative estimates put the halo radius at 250,000 light-years. That is the virial radius where material is gravitationally bound to the galaxy. But some models suggest the halo extends much farther. 400,000 light-years. 600,000. Some calculations push it past 1 million light-years. 1 million light-years. If true, that makes the Milky Way 20 times wider than the old textbook measurements. 20 times more space under our gravitational control. Picture the scale. Andromeda sits 2.5 million light-years away. If our dark matter halo reaches 1 million light-years out, and Andromeda's halo does the same, only 500,000 light-years of truly empty space separates us. The halos might already be touching. 2 invisible clouds of dark matter interpenetrating, mixing, preparing for the eventual collision. We cannot see the halo directly. Dark matter does not emit light, does not absorb light, does not interact with electromagnetic radiation at all. It only interacts through gravity. But that gravity is real, measurable, powerful. Researchers map the halo using indirect methods. Satellite galaxy orbits reveal where mass concentrates. Gravitational lensing shows where space curves. Computer simulations predict how dark matter should distribute based on galaxy. You are inside the halo right now. Dark matter surrounds you, passes through you. Earth is swimming through a sea of dark matter particles, moving at hundreds of miles per second. Trillions of them stream through your body every second. You feel nothing. They pass through normal matter like ghosts. Scientists are trying to detect dark matter directly. Deep underground laboratories wait for a dark matter particle to bounce off a normal atom. So far, nothing. The particles are too shy, too rare, or we are looking in the wrong way. If the halo truly extends 1 million light-years, the Milky Way claims an enormous volume of space. Most of the local group falls within our sphere of influence. We are not just a galaxy. We are a galactic empire, a superstructure of invisible mass dominating everything around us. And if our halo is this large, every other galaxy has one too. The universe is not mostly empty space dotted with galaxies. The universe is mostly dark matter halos with galaxies embedded in their centers like seeds and fruit. Everything we see is a tiny fraction of what exists. The visible universe is decoration on an invisible scaffold. 1 million light-years of darkness. That is the Milky Way. That is home. And we are just beginning to understand how enormous it truly is. The galaxy is spinning too fast. It should fly apart. Stars at the outer edge orbit at speeds that make no sense. They should escape into intergalactic space. They should obey Kepler's laws of motion. They should slow down as you move away from the center. They do not, and nobody fully knows why. Here is the problem. In our solar system, planets farther from the sun orbit slower. Mercury races around in 88 days. Earth takes 365 days. Neptune takes 165 years. The farther out you go, the weaker the sun's gravity, the slower the orbit. This is basic physics. Isaac Newton figured it out 300 years ago. Galaxies should work the same way. Most of the mass sits near the center. Stars farther out should feel weaker gravity. Their orbits should slow down. When you measure their speeds, you should see a nice curve decreasing with distance. Except that is not what happens. Stars at the edge of the galaxy orbit at nearly the same speed as stars closer in. The rotation curve stays flat. This is impossible unless there is more mass out there than we can see. Dark matter. Always dark matter. The invisible halo provides the extra mass. It extends far beyond the visible stars, keeping outer objects moving fast. The flat rotation curve is the smoking gun. The proof that dark matter exists in huge quantities. But here is where it gets strange. Even accounting for dark matter, the speeds are higher than predicted. Some stars in the outer halo move at 130 miles per second. Others hit 150. These velocities are barely below escape velocity. The stars are almost fast enough to leave the galaxy entirely. Why do they orbit so close to the edge of escape? What fine-tuned mechanism keeps them bound but barely? This is called the escape velocity problem, and it haunts astronomers. One possibility is that we still underestimate the galaxy's mass. Maybe there is even more dark matter than current models suggest. Maybe the halo is denser at the edges than we think. Maybe our mass calculations are still wrong. Another possibility is that the galaxy recently grew. If the Milky Way devoured a large dwarf galaxy in the past few billion years, the merger could have injected stars into fast orbits. These stars have not had time to settle into stable paths. They still carry the energy from the collision. Evidence supports this idea. The Sagittarius dwarf is being torn apart right now. Its stars are scattering into the Milky Way's halo at high speeds. In a billion years, those stars will look like native halo stars. Fast, barely bound, mysterious. But what comes next is even stranger. Some stars move too slow. Hypervelocity stars in reverse. Objects that should orbit faster based on their location but do not. They drift along like they are trapped in molasses. Nobody has a good explanation for these either. The rotation curve should be simple. Measure speeds. Calculate mass. Everything fits. Instead, every new measurement reveals more anomalies, more outliers, more stars doing things they should not be able to do. This is where dark matter theories get tested. Different models predict different rotation curves. Warm dark matter produces smoother profiles. Cold dark matter creates lumpier structures. Self-interacting dark matter behaves differently in galactic cores. So far, cold dark matter fits best. But the fit is not perfect. Discrepancies remain. Small ones. Nagging ones. The kind that might point toward new physics or might just be measurement error. The galaxy spins faster than it should. Stars orbit at speeds that defy simple explanations. And the larger galactic size makes the problem worse. More volume, more stars, more weird velocities to explain. Physics works everywhere else in the universe. It works in solar systems, in star clusters, in galaxies far away. But in our own backyard, in the Milky Way's rotation curve, something is still not quite adding up. The Milky Way has 4 major spiral arms. Or maybe 5. Or maybe 6. Astronomers are still arguing. For decades, the textbook answer was 4 arms. Scutum Centaurus, Norma Cygnus, Perseus, Sagittarius. Each arm, a river of stars, gas, and dust spiraling outward from the galactic center. These arms trace regions where new stars are born. Bright, dense, easy to spot. Then, better telescopes arrived. Infrared instruments that see through dust. Radio telescopes that map hydrogen gas. Space-based observatories above atmospheric interference. Each new tool revealed features we missed before. The far 3 kiloparsec arm appeared first, a minor spiral arm hiding behind the galactic core. We could not see it with optical telescopes because the center blocks the view. But infrared instruments cut through the dust. There it was, an entire arm thousands of light years long, right under our noses. Then came hints of other structures. The local arm where our solar system sits might actually be a major arm, not just a minor spur. New observations suggest it connects to larger structures farther out. What we thought was a branch might be a whole limb. The outer arm posed another mystery. It sits at the extreme edge of the visible galaxy. Some researchers thought it was just scattered stars. No real structure, but detailed mapping revealed organized spiral patterns extending far into the outer regions. The galaxy has structure where we thought it was empty. But here is the truly bizarre part. Nobody knows how spiral arms form. We see them in almost every disk galaxy. Beautiful, elegant spirals. But the physics behind them remains murky. Here is the problem. Stars orbit the galactic center at different speeds. Inner stars orbit faster. Outer stars orbit slower. If spiral arms were just concentrations of stars, they would wind tighter and tighter over time, like stirring cream into coffee. Within a few rotations, the arms should blur into a smooth disk. They do not. Spiral arms persist for billions of years. This suggests they are not material structures. They are density waves, regions where stars temporarily bunch up, creating the illusion of an arm, like cars bunching in a traffic jam. The cars move through the jam, but the jam stays in place. Density wave theory works mathematically, but observations keep finding exceptions. Some arms have too many young stars. Others show gaps where stars should be. The outer arm appears too massive to be just a wave. It might be real structure, material pulled out during a galactic collision millions of years ago. The bigger Milky Way's size complicates everything. More space means more room for structure. Arms can extend farther. New arms can form in regions we thought were empty. The spiral pattern becomes more complex. Recent surveys using the Gaia spacecraft mapped 1 billion stars with incredible precision. The data revealed substructure within the arms, branches, spurs, gaps. The spiral pattern is not clean. It is messy, chaotic, like tree branches growing in every direction. Some researchers now argue the Milky Way is not a grand design spiral at all. It might be a flocculent spiral, a galaxy with patchy, poorly defined arms. This would explain why different surveys find different arm counts. Everyone sees different features depending on what they measure. The debate continues. More telescopes, more data, more arguments at conferences. But one thing is certain. The Milky Way is more complex than the simple four-arm diagram in textbooks. Hidden structures fill the galaxy, arms we missed for decades. And if we missed entire spiral arms in our own galaxy, what else have we overlooked? What other features hide in the darkness, waiting for the right instrument to reveal them? Draw a line marking the edge of the galaxy. Sounds simple. It is impossible. Galaxies do not have boundaries like countries or continents. No border wall, no sign saying, now leaving the Milky Way. Stars just thin out gradually, slowly, until there are none, or maybe a few scattered stragglers. Where exactly does that become not the galaxy? This is not a philosophical question. It is a practical problem. Astronomers need a definition, a standard measurement, a way to compare galaxies. But nature does not cooperate. The universe does not care about our need for clean categories. Several definitions exist, none of them perfect. The optical radius marks where visible stars become too faint to see. This gives you the bright disk, the obvious part. 100,000 light-years for the Milky Way. But this ignores all the faint stars, dim dwarfs, and scattered halo objects. It is like measuring a city by counting skyscrapers and ignoring all the houses. The virial radius is more scientific. It marks where objects are gravitationally bound to the galaxy. Inside this radius, stars orbit the center. Outside, they drift freely. For the Milky Way, this gives about 250,000 light-years. Much better. But even this has problems. Some stars outside the virial radius still move with the galaxy. They share our motion through space. They formed here. Are they part of the galaxy or not? The virial radius says no. Common sense says maybe. Then there is the dark matter halo. It extends far beyond everything else. If the halo reaches 1 million light-years out, is that the real edge? Most astronomers say no. The halo fades so gradually that choosing any boundary is arbitrary. It is like trying to mark where Earth's atmosphere ends. Technically, it extends thousands of miles up. Practically, it is gone after 100 miles. Where do you draw the situation gets worse when you consider galactic winds. The Milky Way produces massive outflows of gas. Supernovae explode. Stars shed material. This gas blows outward into intergalactic space. Hundreds of thousands of light-years out. Is that material still part of the galaxy? Some of it will fall back. Gravity pulls it down. The galaxy recycles its gas over billions of years. But some escapes forever, lost to the void. At what point does gas stop being Milky Way gas and become intergalactic medium? The Magellanic Stream adds another complication. The large and small Magellanic Clouds are leaking gas as they orbit us. This gas forms a stream stretching across the sky. Is that stream part of the Magellanic Clouds, part of the Milky Way, or neither? All three answers have defenders. Andromeda poses the same problem from the other direction. Its dark matter halo might already be touching ours. When two halos overlap, where does one galaxy end and the other begin? The space between becomes shared territory, co-owned, disputed. This is not just semantics. The definition affects mass estimates. It affects size comparisons. It affects our understanding of when the Andromeda collision truly begins. If the halos are already merging, the collision started millions of years ago. We are living inside it. Most astronomers settle on practical definitions. The disk ends where star formation stops. The halo ends at the virial radius. The dark matter extends as far as simulations suggest. Each definition serves different purposes. None of them perfectly captures reality. Here is the truth. The Milky Way is not an object. It is a region, a zone of influence, a gravitational neighborhood. It has a dense core, a structured middle, a diffuse edge, and beyond that edge it fades into something else. 200,000 light-years is our current best answer. But ask that question again in 10 years. New measurements will change it. They always do. The galaxy has no edge because the universe does not work that way. Everything blends. Everything connects. We live in a cosmos without borders, and we are still learning to measure it. There are stars at the very edge of the galaxy moving at insane speeds. 130 miles per second. 150. Some hit 200. They should escape. They should fly off into intergalactic space. They do not. Something holds them. These are called high-velocity halo stars, not hypervelocity stars which move fast enough to escape. Halo stars move just under that threshold, barely bound, skating on the edge of freedom. Finding them was difficult. They are faint, distant, scattered across a huge volume. But surveys like Gaia tracked millions of stars with incredible precision. Measure position, measure motion, calculate velocity. Some stars lit up red flags immediately. One star, traveling through the outer halo, moves at 198 miles per second. The galaxy's escape velocity at that location is roughly 200 miles per second. This star is 2 miles per second away from leaving forever. It is like a rocket barely held by Earth's gravity. One small push and it is gone. Why do so many stars orbit so close to escape velocity? This is not random chance. Something put them there. Something gave them that specific amount of energy. But what? Galactic collisions offer one answer. When the Milky Way ate smaller galaxies, the collisions injected energy into the system. Stars from the dwarf galaxy received huge velocity kicks. Some escaped. Others settled into fast, barely bound orbits. These survivors now populate the halo. The Sagittarius dwarf provides evidence. Its stars are scattering at high speeds as the Milky Way tears it apart. In 1 billion years, those stars will be indistinguishable from other halo stars. Fast, ancient, mysterious. But we caught this one in the act. We see it happening. Another possibility involves three-body interactions. When two stars pass near a third object, gravitational interactions can fling one star outward at high speed. This happens in dense star clusters. Occasionally, a star gets ejected with enough energy to reach the galactic halo. Most escape. A few land in that sweet spot. Fast but not too fast. Black holes complicate everything. If a star passes close to a massive black hole, the gravitational slingshot can accelerate it to enormous speeds. The supermassive black hole at the galaxy's center weighs 4 million suns. Any star venturing too close either gets eaten or flung away violently. We found several hypervelocity stars leaving the galaxy at speeds over 400 miles per second. These stars are escaping, no question. Calculations trace their paths back to the galactic center. Something near the black hole kicked them out. Maybe they were in binary pairs and the black hole captured one star while ejecting the other. But the barely bound stars pose a different puzzle. They are not coming from the center. They orbit far out in the halo. Their speeds are high but not extreme. They seem comfortable at the edge of the galaxy's gravitational well. One theory suggests the dark matter halo is lumpier than we think. Concentrations of dark matter at specific distances could create stable orbits at high velocities. Stars settle into these orbits naturally. This would explain why so many halo stars move at similar speeds. They are trapped in resonance with the dark matter distribution. Testing this theory is hard. We cannot see dark matter directly. We can only infer its distribution from how stars move. But if the halo is lumpy, we should see groupings, clusters of high-velocity stars orbiting together. Some surveys hint at this. Others find random distributions. The data is messy. Here is what we know for certain. The galaxy's outer regions are wilder than expected. Stars move faster than simple models predict. The boundary between bound and unbound is thin. Barely a few miles per second separates staying and leaving. If the galaxy is larger than we thought, more stars live in this dangerous zone. More objects skating at the edge, more potential escapees. And understanding why they stay reveals something deep about galactic structure, about dark matter, about how gravity works at enormous scales. Fast stars at the edge of the galaxy, held by invisible mass, moving at impossible speeds. And we are only beginning to understand what keeps them here. The Milky Way is not special. If we measured our galaxy wrong, we measured all galaxies wrong. This is the terrifying implication, the realization that makes astronomers stay up at night, recalculating everything they thought they knew. Every galaxy in the universe might be twice as large as recorded. The cosmic census needs rewriting. Here is why this matters. Astronomers use galaxies to understand the how matter distributes, how structure forms, how dark energy affects cosmic expansion. If the galaxies are all bigger than we thought, every calculation changes. Galaxy masses determine how they interact. Bigger galaxies have stronger gravity. They strip stars from smaller neighbors more easily. They dominate their local groups more completely. They form clusters differently. Recalculate masses and you recalculate galaxy evolution. The problem extends to distance measurements. Astronomers use certain types of galaxies as standard candles. Objects with known brightness measure how bright they appear, calculate how far away they must be. But if those galaxies are bigger, their brightness changes. The distances change. The expansion rate of the universe changes. Dark energy measurements depend on precise distance calculations. Any error propagates through every cosmological model. If galaxies are universally larger, dark energy calculations shift. The universe might be expanding faster or slower than we think. Researchers are now revisiting galaxy surveys. The Sloan Digital Sky Survey, the 2-micron All-Sky Survey, every major catalog, they are applying new measurement techniques, accounting for dark matter halos using stellar streams and satellite galaxies where available. Preliminary results are disturbing. Many galaxies appear larger, some by 50%, others by a factor of 2. The trend is consistent. We systematically underestimated galactic size. Andromeda is bigger. Triangulum is bigger. Every major galaxy in the local group needs remeasurement. And if local galaxies are bigger, distant galaxies probably are too. The whole cosmic web might be denser than we realized. This has implications for dark matter. If galaxies are bigger, they contain more dark matter. The ratio of dark matter to normal matter shifts. This affects theories of galaxy formation. It affects predictions about how the universe evolved. It affects whether our cosmological models even work. Some researchers suggest the discrepancy explains long-standing problems. The missing satellite problem, for example. Simulations predict large galaxies should have hundreds of satellite galaxies orbiting them. We only observe dozens. If our galaxy is bigger, its gravity pulls farther. Maybe those missing satellites exist, but orbit so far out we have not found them yet. Another puzzle involves galaxy rotation curves. Many galaxies show the same flat rotation pattern as the Milky Way. Stars at the edge orbit too fast. This is why dark matter was hypothesized in the first place. But if the galaxies are bigger, the dark matter halos extend farther. The rotation curves make more sense. The physics fits better. But recounting creates new problems. If galaxies are bigger, the space between them is smaller. The universe becomes more crowded. Galaxy interactions happen more often. Collisions occur sooner. The timeline of cosmic evolution speeds up. This affects our understanding of galaxy clusters. Large groups of galaxies bound by gravity. If each galaxy is bigger, their gravitational interactions become more complex. The cluster dynamics change. Mass estimates shift. Dark matter distributions need recalculating. Even the very early universe gets affected. Astronomers use distant galaxies to study cosmic history. Galaxies forming billions of years ago. If those primordial galaxies were larger than measured, they formed faster than we thought. Structure assembled more quickly. The universe was more mature at earlier times than our models suggest. The implications cascade through every field of astronomy. Stellar population studies, galaxy morphology, active galactic nuclei, supermassive black hole evolution. Everything connects to size. We are recounting the universe. Every galaxy, every cluster, every structure, starting from scratch with better measurements. And the universe that emerges is bigger, denser, and more complex than we imagined. The Milky Way was just the beginning, the first domino, and the rest are falling. The Milky Way spins around a point, not the supermassive black hole, not the visible core, the center of mass. And we just realized that point is not where we thought it was. Center of mass is simple in principle. It is the balance point, the spot where all the mass averages out. For a ruler, it is the middle. For Earth and Moon, it is a point inside Earth but offset from the center because the Moon pulls. For the galaxy, it is the location around which everything orbits. Astronomers assumed the center of mass sat at the galactic core. Makes sense. Most of the visible stars cluster there. The supermassive black hole sits there. Everything seems to point toward the center. But that assumption ignored dark matter. Dark matter does not concentrate at the core. It forms a massive halo around the entire galaxy. This halo is not perfectly symmetric. It is lumpy, denser in some directions, thinner in others. The distribution of dark matter shifts the center of mass away from the visible center. When scientists recalculated using the larger galactic size and updated dark matter distributions, the center of mass moved. Not dramatically, not thousands of light years, but enough to matter. A few hundred light years, maybe 1,000. This sounds small. In human terms, it is enormous. The center of mass shifted farther than the entire distance from Earth to the nearest star. Farther than dozens of solar systems lined up end to end. Why does this matter? Everything orbits the center of mass, not the visible center. Stellar orbits depend on where the true balance point sits. Satellite galaxies orbit around this point. The motions of stars near the core reveal the center of mass location. Measuring this shift is difficult. You need precise velocities for stars throughout the galaxy. You need accurate dark matter maps. You need computer simulations to model the entire gravitational field. Only recently have instruments been good enough to detect the offset. The Gaia spacecraft provided the breakthrough. It measured positions and velocities for over 1 billion stars with incredible precision. Researchers fed this data into simulations and calculated the gravitational center. The results were surprising. The center of mass does not align perfectly with the supermassive black hole. This has implications for our orbit. The solar system orbits the galactic center once every 230 million years. A galactic year. But if the center of mass is offset, our actual orbital path is slightly different than calculated. We might complete an orbit a little faster or slower than previously thought. The offset also affects how we model the galaxy. Simulations assume perfect symmetry for simplicity. A core at the center. Dark matter distributed evenly around it. But reality is messier. The Milky Way likely formed through mergers with smaller galaxies. Those collisions left scars. Asymmetries in the dark matter distribution offset mass concentrations. The Sagittarius dwarf is currently falling into the Milky Way. As it gets torn apart, its mass affects our center of gravity. Not by much. The dwarf is small compared to the entire galaxy. But over millions of years, these interactions shift the balance point around. Some researchers suggest the center of mass oscillates. It moves back and forth slightly as galaxies fall in and get digested. The Milky Way is not a static structure. It is dynamic, constantly evolving, constantly eating, and every meal shifts the balance. Here is the strangest part. If the center of mass is offset from the black hole, what does that mean for the black hole itself? Supermassive black holes are supposed to sit at galactic centers because they form there. They grow by eating material that falls toward the center of mass. If the center of mass is elsewhere, why is the black hole where it is? One possibility is that black hole predates the current galactic structure. It formed when the galaxy was smaller and more symmetric. As the Milky Way grew through mergers, the mass distribution changed. The center of mass shifted, but the black hole stayed put because it is so massive. Nothing can easily move 4 million solar masses. Another possibility is that the offset is temporary. Over billions of years, the galaxy will settle into a more symmetric state. The center of mass will drift back toward the core. The black hole will remain at the center. Equilibrium will be restored. But for now, in this snapshot of galactic evolution, the balance point is slightly askew. The Milky Way spins around a point that is not quite where we expected. The galaxy just got bigger. And with that growth came a shift. A subtle change in the center of everything. small in cosmic terms, enormous in human terms, and we are only beginning to measure what that shift means. Galaxy collisions are not what you think. No explosions, no fireballs, no dramatic crashes, just slow-motion gravitational ballet stretching across hundreds of millions of years. But scale changes everything. A bigger galaxy collides differently than a small one. The physics stays the same. The outcomes transform completely. When two small galaxies collide, the interaction is relatively quick. A few 100 million years, maybe a billion. They merge, settle, and move on. But when two massive galaxies like the Milky Way and Andromeda collide, the process takes longer. Much longer. The increased mass means stronger gravity. Stronger gravity means more complex interactions. Here is what happens in a large galaxy collision. First contact occurs when the dark matter halos touch. This happens long before the visible disks interact. The halos extend hundreds of thousands of light years outward. When they meet, gravity begins its work. The halos interpenetrate. Dark matter particles pass through each other like ghosts. They do not collide physically. They do not bounce. They simply occupy the same space. But their gravity affects everything. Stars field pools from both galactic centers. Orbits destabilize. Chaos begins. Next, the outer stellar halos interact. Stars in these regions are already moving fast, barely bound. When another massive galaxy approaches, some stars get flung into intergalactic space. Ejected, lost forever, others get captured by the approaching galaxy. Stolen. The galaxies start exchanging stars like trading cards. Then come tidal forces. As the galaxies pass each other, gravity pulls harder on the near side than the far side. This difference stretches both galaxies. Material gets pulled into long streamers called tidal tails. These tails can extend millions of light years into space. Beautiful. Destructive. Proof that giants fought here. The visible disks collide last. When they meet, something remarkable happens. The gas clouds in both galaxies compress. Compressed gas collapses. Collapsed gas forms stars. Star formation explodes across both galaxies. Millions of new stars ignite in a cosmic fireworks display. Astronomers call these starburst galaxies. Collisions in progress. But here is where size matters most. Bigger galaxies have deeper gravitational wells, harder to escape from. When material gets pulled into tidal tails, more of it falls back. Smaller galaxies lose material permanently. Larger galaxies recycle it. The Milky Way and Andromeda will shed stars during collision. But most will eventually return. The merger timeline stretches longer too. Small galaxies might complete their merger in 1 or 2 passes. Large galaxies orbit each other multiple times. 3 passes. 4. Maybe 5. Each orbit strips away more material. Each pass drives the cores closer together. Eventually, friction from gas and stars drains orbital energy. The galaxies spiral inward. The cores merge. The final product depends on mass ratio. When 2 equal mass giants collide, you get a massive elliptical galaxy. The spiral structure is destroyed completely. Disk stars get scrambled into random orbits. No more elegant spirals. Just a blob of stars moving chaotically. Milkomeda, our future merged galaxy, will be enormous. 800 billion stars. 4 trillion solar masses, one of the largest galaxies in the local group. A true heavyweight, but the collision also triggers other effects. The supermassive black holes at each galactic center will merge. 4 million solar masses plus 1 billion solar masses from Andromeda equals one massive black hole at the heart of Milkomeda. This merger will release gravitational waves detectable across the universe. Star formation will spike, then crash. The initial collision ignites millions of new stars. But the merger consumes most of the available gas. After a few billion years, star formation stops. Milkomeda becomes a red and dead galaxy. Old stars. No new ones. Slowly fading. Bigger galaxies collide differently. Longer timelines. More complex interactions. More dramatic outcomes. And we are watching the preview. The Milky Way and Andromeda are already beginning their dance. The halos might already be touching. First contact may have already occurred. The collision is not coming. It has begun. And scale determines how the story ends. There is mass we cannot account for. Material that should be there but is not. Astronomers call it the missing mass problem. And it just got 3 times worse. Here is the issue. When you add up all the visible matter in the galaxy, you get about 200 billion solar masses. Stars, planets, gas clouds, dust, everything we can see. They're needed. Simulations say galaxies should contain a specific amount of baryonic matter, based on the cosmic ratio. But when we count stars, gas, and dust, we come up short. Way short. About half the expected baryons are missing. Where did they go? Several possibilities exist. Theory 1 suggests the missing baryons were ejected. Supernovae explode. Stars produce powerful winds. Active galactic nuclei blast out material. Over billions of years, this outflow could have expelled enormous amounts of gas into intergalactic space. The baryons are not missing. They are just outside the galaxy now. Too diffused to detect easily. Theory 2 proposes the baryons are hiding. Maybe they exist as cold gas clouds too faint to see, or as dim brown dwarfs too small to shine, or as rogue planets drifting through interstellar space. They are there. We just cannot find them with current instruments. Theory 3 gets weird. Maybe the baryons were never in the galaxy at all. Maybe they are stuck in the intergalactic medium. The space between galaxies contains thin gas. Extremely thin. But across enormous volumes it adds up. Perhaps half the universe's baryons are floating in this medium, never falling into galaxies. Recent observations favor Theory 1. X-ray. Telescopes detected hot gas halos around galaxies. This gas is too hot to form stars, but too diffused to see easily. It exists in a weird intermediate state, ionized, energetic, invisible to most instruments, but it is there, and there is a lot of it. When scientists measured these hot halos, they found significant mass, enough to account for much of the missing baryons. Maybe the problem was solved, except the Milky Way just got bigger, which means it should have even more baryons, and we still cannot find them all. A 4 trillion solar mass galaxy needs a specific amount of normal matter based on cosmic ratios. About 400 billion solar masses of baryons. We see maybe 200 billion in stars and gas. The rest? Missing. Again. Tripling the galactic mass triples the missing mass problem. If the galaxy is twice as wide and much more massive, Where did all that extra baryonic matter go? It should be somewhere. In the halo, in the disk, in orbit, but we cannot find it. Some researchers suggest the dark matter halo traps hot gas at enormous distances, hundreds of thousands of light years out. This gas is so hot and diffused that current X-ray telescopes barely detect it. But it carries significant mass. Future missions with better sensitivity might reveal enormous reservoirs of missing baryons hiding in plain sight. Another possibility involves the circumgalactic medium, the zone around the galaxy where material cycles in and out. Gas ejected by supernovae flows outward, cools, falls back. This recycling process creates a massive reservoir of baryons surrounding the galaxy. Not quite inside, not quite outside. Transitional. The James Webb Space Telescope is hunting for these baryons now. Its infrared sensitivity can detect warm gas that other instruments miss. Early results hint at more material in the outer halo than previous surveys suggested. But we need more data, more observations, more time. Here is the unsettling truth. We live in a galaxy where we cannot account for half the normal matter. We know roughly where dark matter is. That is the easy part. But regular matter, the stuff we are made of, keeps hiding from us. A bigger galaxy means a bigger mystery. More missing mass. More unanswered questions. And somewhere in the darkness, 400 billion solar masses of normal matter are waiting to be found. The Milky Way is not special. This fact keeps appearing in astronomy. Every time we think we are unique, we discover everyone else is the same. And if our galaxy is twice as large as measured, spiral galaxies everywhere face the same miscalculation. Researchers tested this hypothesis. They selected a sample of nearby spiral galaxies. Andromeda, Triangulum, galaxies close enough for detailed observation. Then they applied the new measurement techniques: satellite galaxy tracking, stellar stream mapping, dark matter halo calculations. Every single galaxy came back larger. Not just a little, significantly. 50% bigger on average. Some doubled in size just like the Milky Way. The pattern was universal. We systematically underestimated spiral galaxy sizes across the board. Andromeda provided the clearest example. The old measurements said 220,000 light-years across. New calculations suggest 300,000. Maybe more. The dark matter halo extends even farther. Andromeda is a giant, even bigger than previously thought. Triangulum, the third largest galaxy in the local group, grew from 60,000 light-years to nearly 100,000. Smaller galaxies showed similar increases. NGC 5204, NGC 2976. Every spiral examined came back larger. Why did this happen? The same reason we got the Milky Way wrong. Old measurements focused on visible light. They tracked the bright disk where stars concentrate. They ignored the faint outer regions. They underestimated dark matter contributions. The mistake was systematic, built into the methodology. Modern instruments changed everything. Wide-field surveys map entire galaxies edge to edge. Infrared detectors see through dust. Deep exposures reveal faint outer stars. Each improvement extends the radius outward. But the real breakthrough came from satellite galaxies. Just like the Milky Way has satellites, other large spirals do too. Andromeda has dozens of dwarf companions. Triangulum has several. Track those satellites, measure their orbits, calculate the mass holding them. The galaxies reveal their true sizes. Stellar streams appear everywhere too. Andromeda is currently devouring several small galaxies. The resulting streams wrap around it like evidence at a crime scene. These streams orbit far beyond the visible disk, proving Andromeda's gravity reaches farther than old measurements suggested. Dark matter halos extend farther than anyone predicted. When you account for the full halo, not just the inner dense regions, spiral galaxies become enormous. Their spheres of influence reach hundreds of thousands of light-years. The space between galaxies shrinks accordingly. This discovery has cascading implications. Galaxy collision rates need recalculation. If galaxies are bigger, their halos overlap more often. Interactions happen more frequently. The universe becomes more violent, more dynamic. Galaxy number density changes too. The same volume of space contains fewer galaxies if each galaxy is larger. This affects cosmological models. It shifts our understanding of structure formation. It changes predictions about how galaxy clusters evolve. Rotation curves make more sense now. Many spiral galaxies show flat rotation curves like the Milky Way. Stars at the edge orbit too fast. But if the galaxies are bigger, with more extensive dark matter halos, the rotation curves fit better. The physics works. Some researchers wondered if dwarf galaxies follow the same pattern. Early results suggest they do. Even small galaxies appear larger than measured. Their dark matter halos extend farther than their visible stars. The size underestimation affects galaxies at every scale. Elliptical galaxies remain less clear. They do not have obvious disks or spiral arms. Measuring their edges is even harder. But preliminary work suggests they are also larger than traditional estimates. The problem is universal. Here is the bottom line. For decades, astronomers measured spiral galaxies using incomplete methods. They counted what they could see. They drew boundaries where stars became faint. They made reasonable assumptions that turned out wrong. Every spiral galaxy in the universe is larger than textbooks show. Not just ours. All of them. The cosmic census needs complete revision, and we are only beginning to understand how much bigger everything truly is. The local group of just shrank. Not physically, conceptually. The space between galaxies is smaller because the galaxies themselves are bigger. The local group is our cosmic neighborhood. A gravitationally bound cluster of galaxies dominated by three giants. The Milky Way, Andromeda, Triangulum, plus dozens of smaller dwarfs orbiting around them. Total population about 80 galaxies within a 10 million light-year radius. Or so we thought. The boundaries need redrawing. When galaxies are bigger, their gravitational influence extends farther. The sphere of control grows. Territory that seemed like neutral intergalactic space actually belongs to one galaxy or another. The no man's land between giants shrinks. Andromeda sits 2.5 million light-years away. The old measurement showed our disks separated by 2.5 million light-years of empty space. But with updated sizes, the picture changes. Our dark matter halo extends at least 250,000 light-years out, maybe farther. Andromeda's halo does the same, possibly larger. Subtract those halos from the total distance. 2.5 million minus 500,000. Only 2 million light-years of truly neutral space separates us. less if the halos extend farther. Some models suggest they might already be touching. The collision could have already begun in the invisible dark matter realm. This changes group dynamics. The local group is not three separate entities with space between them. It is three overlapping spheres of influence. The boundaries blur. Territory becomes contested. Some dwarf galaxies orbit in regions claimed by multiple large galaxies. Take the Magellanic Clouds. Are they satellites of the Milky Way or just passing through? Old measurements suggested they might escape eventually. New calculations say no, our gravity reaches farther. The clouds are trapped. Permanent prisoners. In a few billion years, we will devour them completely. Several dwarf galaxies sit in the space between us and Andromeda. Which galaxy do they belong to? Technically, they orbit in the combined gravitational field of both. They feel pulls from multiple directions. As the Milky Way and Andromeda approach each other, these dwarfs will get caught in the middle. Torn apart. Scattered. Casualties of a galactic war. Triangulum faces a similar fate. It is the third largest galaxy in the local group, but barely. About 60 billion stars. New measurements suggest it might already be falling into Andromeda. The distance between them is only about 750,000 light-years. With updated halo sizes, they are practically touching. Triangulum is not an independent galaxy. It is a satellite of Andromeda or will be soon. Redrawing boundaries affects how we count galaxies. Some objects we thought were independent turn out to be satellites. Others we thought were satellites might be independent. The total number of galaxies in the local group stays about 80, but the categorization changes. The group center of mass shifts too. With larger galaxy sizes and updated masses, the gravitational balance point moves. It sits somewhere between the Milky Way and Andromeda, but closer to Andromeda because Andromeda might be slightly more massive. This point determines how the entire group evolves. Everything orbits around it. Everything falls toward it. Beyond the local group, boundaries with neighboring groups need revision too. The Sculptor group sits about 12 million light-years away. The Maffei group is closer but obscured by the Milky Way's disk. These neighboring clusters have their own gravitational zones. With bigger galaxies, those zones expand. The space between groups shrinks. Some astronomers now suggest the local group is larger than traditionally defined, maybe 15 million light-years across instead of 10. The outer members orbit farther out than we realized. The group claims more territory. More space falls under its gravitational control. This matters for understanding cosmic structure. Galaxy groups cluster into superclusters. The local group belongs to the Virgo supercluster, or possibly the larger Laniakea supercluster, depending on how you define boundaries. If groups are larger, superclusters reorganize. The hierarchy of cosmic structure shifts at every level. Here is the strange part. Boundaries are arbitrary. Galaxies do not respect imaginary lines. They blur together, overlap, merge. The concept of separate objects is a human construct. Nature sees continuous fields of gravity, smooth gradients of density, no walls, no borders. The local group is not a collection of isolated galaxies. It is one big gravitational basin with concentrations of matter we call galaxies. Redraw the boundaries all you want. The truth is messier than any map can show. And we are living inside that mess, trying to chart territory that refuses to be charted. The star count just doubled. The Milky Way contains approximately 400 billion stars, maybe more. Every estimate doubled along with the galactic size. 400 billion. The number is incomprehensible. If you counted one star per second, it would take 12,700 years to count them all. Longer than recorded human history, and you would still have billions left. Compare that to Earth's population. 8 billion humans. We would need 50 Earths worth of people to match the number of stars in this galaxy. 50 entire planets full of humans. That is how many stars we are talking about. Old estimates said 200 billion. They were wrong. The mistake came from sampling. Astronomers counted stars in small regions, then extrapolated. They measured the neighborhood, counted stars per cubic light year, multiplied by the galaxy's volume. Simple. Except the galaxy's volume was wrong. Double the radius and you increase volume by a factor of 8. Twice as wide means 8 times more space. Not all that space is filled with stars. The outer regions are sparse. But even sparse regions contribute. Add up all the extra volume and you get billions more stars. Most of the new stars are red dwarfs. Small, dim, long-lived. These stars make up about 70% of all stars, but contribute barely any light. You can have a billion red dwarfs in a region and it still looks dark. They hide in plain sight. The outer halo contains more stars than previously thought. Old surveys missed them because they are faint and scattered, but modern instruments with better sensitivity reveal them. Hundreds of millions of halo stars orbiting far from the galactic disk. Ancient stars. Metal-poor stars. Survivors from the galaxy's earliest days. Then, there are the stars we devoured. Every time the Milky Way ate a smaller galaxy, it absorbed that galaxy's stars. Those stars still exist. They orbit within our halo now. Former citizens of destroyed civilizations. Immigrants forced into our galaxy by gravity. The Sagittarius dwarf alone contributed tens of millions of stars. The stream wrapping around the galaxy contains about 100 million stars. Those are all new additions to the Milky Way census. Former Sagittarius citizens now counted as ours. 400 billion stars means 400 billion chances for planets. Not every star has planets, but many do. Maybe most do. Conservative estimates suggest 60% of stars have at least one planet. That is 240 billion planets. Minimum. How many are habitable? How many orbit in the zone where liquid water can exist? Estimates vary wildly. Conservative guesses say 1% of planets are potentially habitable. That is 2.4 billion habitable worlds. In our galaxy alone, just got doubled from previous estimates. Even if life is incredibly rare, 1 in a million habitable planets, that still leaves 2,400 worlds with life in the Milky Way. Double what we thought before. And if intelligent life is rarer still, 1 in a billion planets, we still have 2 or 3 civilizations out there somewhere. The Drake equation calculates the number of communicative civilizations. Every variable in that equation just increased. More stars, more planets, more chances. The probability of finding alien intelligence went up significantly. Not guaranteed, but more likely. Here is the uncomfortable question. If there are 400 billion stars and we only know a fraction of them, what is hiding in the data? What strange objects lurk in the outer halo? Rogue planets, failed stars, black holes, neutron stars, objects we have never even imagined. Every star has a story, a birth in a collapsing gas cloud, a life burning hydrogen, an eventual death as a white dwarf, neutron star, or black hole. 400 billion stories, 400 billion lifetimes playing out right now across the galaxy. The Sun is one of 400 billion. Average, unremarkable. One voice in a choir so large no one can hear individual notes. We are not special. We are not unique. We are one star system among hundreds of billions. And that number just doubled. The galaxy just got twice as crowded, which makes our cosmic loneliness even stranger. With so many stars, so many planets, so many chances, where is everybody? 400 billion stars, and we have not heard from any of them. Yet, double the stars, double the planets, double the chance that we are not alone. The bigger Milky Way fundamentally changes the search for extraterrestrial life. Start with habitable zones. Each star has a region where planets receive just the right amount of heat for liquid water. Too close and water boils away. Too far and it freezes solid. This zone shifts based on the star's size and temperature. Red dwarfs have tiny habitable zones close to the star. Sun-like stars have zones similar to Earth's orbit. Giants have zones farther out. 400 billion stars mean 400 billion potential habitable zones. Not all of them host planets, but many do. The Kepler Space Telescope discovered that planets are common, extremely common. Most stars have at least one planet. Many have multiple planets. Planetary systems are the rule, not the exception. Estimate conservatively. Say 60% of stars have planets. That is 240 billion planetary systems. Now estimate what fraction of those systems have planets in the habitable zone. Maybe 10%. That gives 24 billion potentially habitable planets in our galaxy alone, just doubled from previous estimates. But habitable does not mean inhabited. Planet can have liquid water and still be sterile, dead, empty. Life requires more than just water. It needs the right chemistry, the right energy sources, the right conditions over billions of years. How rare is life? Nobody knows. We have one data point, Earth. That is it. Everything else is speculation. Some scientists think life is inevitable given the right conditions. Others think it is vanishingly rare, a cosmic accident, a 1 in a trillion fluke. Let us assume life is moderately rare. 1 in 1,000 habitable planets develops life. That is still 24 million living worlds in the Milky Way, doubled from previous estimates. 24 million planets where biology exists, where cells divide, where evolution operates, where organisms adapt and survive. Most of that life is probably simple. Bacteria, single cells, slime. Intelligence is rarer. Earth existed for 3 billion years with only microbes. Complex multicellular life appeared relatively recently. Intelligence showed up yesterday in geological time. If intelligence is 1 in a million among living worlds, that gives us 24 intelligent species in the galaxy. Maybe more, maybe less. The numbers are uncertain. But doubling the galaxy size doubled the probability. Whatever the true number, it just increased by a factor of 2. The Fermi paradox gets more intense. If there are so many chances for life, so many potential civilizations, where is everybody? Why have we not detected signals? Why no alien probes? Why does the galaxy seem empty? Some argue the Great Filter exists, a barrier that prevents civilizations from becoming spacefaring. Maybe it is behind us. Life is hard to start. We got lucky. Or maybe it is ahead of us. Civilizations destroy themselves. Nuclear war, climate collapse, artificial intelligence gone wrong. We are heading toward the filter right now. Others suggest intelligence is even rarer than we think. Maybe we are one of very few. Maybe we are alone in the Milky Way. 400 billion stars and one civilization. Lonely, isolated. The only voices in a silent galaxy. But here is the hopeful perspective. Double the stars means double the chance for contact. If civilized ozone, chemicals that suggest life. The James Webb Space Telescope is already starting this work. Each new habitable planet discovered is one more chance to find life. Twice as many worlds means we are probably not alone. Probably. The probability shifted in favor of life. Not certainty, not proof, but better odds. And better odds mean hope. Somewhere in the Milky Way, orbiting one of 400 billion stars, life might be looking back at us, wondering the same questions, feeling the same loneliness, hoping for contact. The galaxy just got bigger. The chances just got better. And the search continues. Stand at the edge of the Milky Way. Look outward. Where does the galaxy end and intergalactic space begin? The answer is nowhere. There is no edge. Just a gradual fading into darkness. This is the uncomfortable truth. Galaxies do not have borders. They fade. Stars thin out slowly. Dark matter density drops gradually. Gas disperses into the void. At what point does galaxy become not galaxy? The question has no clean answer. Think of Earth's atmosphere. It does not end abruptly. Air pressure decreases with altitude. At sea level, you have one atmosphere of pressure. At 10 miles up, almost none. At 100 miles, practically vacuum. But technically, atmospheric particles exist thousands of miles up. Where does atmosphere end? Arbitrary line based on definitions. The Milky Way works the same way. Star density is highest at the center. About 1 million stars per cubic light-year. Move outward toward the solar neighborhood. 10 stars per cubic light-year. Farther still, 1 star per 10 cubic light-years. At the edge of the halo, 1 star per 1,000 cubic light-years. Keep going. Eventually, you reach 1 star per million cubic light-years per billion, per trillion. The numbers shrink towards zero but never quite reach it. Somewhere out there, isolated stars drift alone. Rogue objects ejected from the galaxy, but not quite in intergalactic space. Do they count as Milky Way stars? Depends on your definition. Dark matter creates the same problem. The halo extends far beyond visible stars. How far? Models suggest at least 250,000 light-years. Maybe 400,000. Possibly 600,000. Eventually, the density drops so low that it blends into the cosmic background. Dark matter exists everywhere. Even intergalactic space contains trace amounts. The transition is smooth, continuous, undefined. Gas clouds blur boundaries further. The Milky Way produces galactic winds. Supernova explosions blow material outward. This gas travels hundreds of thousands of light-years before dispersing. Is that gas part of the galaxy? Came from here. It will eventually fall back. But right now, it exists far beyond any reasonable boundary. The Magellanic Stream illustrates this problem perfectly. Gas stripped from the Magellanic Clouds forms a stream across the sky, about 600,000 light-years long. This gas is not part of the Magellanic Clouds anymore. It is not part of the Milky Way yet. It exists in limbo transitional space. Satellite galaxies add more confusion. They orbit the Milky Way but are considered separate objects. Why? They have their own stars, their own structure, but they are gravitationally bound to us. They will eventually merge with us. Are they part of the Milky Way or not? Both answers work depending on context. The virial radius tries to solve this problem. It defines the boundary where objects are gravitationally bound. Inside this radius, everything orbits together. Outside, objects drift independently. For the Milky Way, this gives about 250,000 light-years. A clean number, a definite boundary, except it is not that clean. Objects outside the virial radius can still feel the Milky Way's gravity. Weak gravity, not strong enough to maintain orbits, but present, measurable, influential. The gravitational field extends indefinitely, fading, never stopping. Light from the Milky Way travels forever. The photons keep moving. They carry information about our galaxy across the universe. In that sense, the Milky Way's influence is infinite. Every star that ever shone here sent light in all directions. That light is still traveling, marking our presence across cosmic distances. Here is what this means practically. When you measure the Milky Way's size, you are making a choice, choosing a definition, deciding what counts and what does not. The 200,000 light-year measurement uses the virial radius. Reasonable, defensible, but not absolute truth. Another astronomer might use a different definition, where star density drops below a threshold, or where dark matter fades to a certain level, or where satellite galaxies stop orbiting. Each definition gives a different size. None of them wrong. None of them perfectly right. The galaxy has no edge because the universe is continuous. Matter distributes smoothly. Density gradients slope gently. Boundaries are human constructs imposed on a cosmos that does not care about categories. We live in a galaxy that fades into nothing. No walls, no boundaries, no clear end. Just a slow transition from dense to empty, from here to nowhere. And measuring that transition is harder than measuring the galaxy itself. The Milky Way is a cannibal. Our galaxy grew to its current size by eating others. Hundreds of smaller galaxies fell into our gravitational well, got torn apart, devoured. Their stars became ours. This is how galaxies grow, not through slow accumulation, through violence, galactic mergers and cannibalism. Bigger galaxies eat smaller ones. The strong dominate, the weak become meals. Survival of the gravitationally massive. Evidence of these ancient meals surrounds us. Stellar streams wrap around the galaxy. Each stream is a corpse, a dwarf galaxy that got too close. The Milky Way ripped it apart, stretching its stars into long ribbons. These ribbons orbit for billions of years before dispersing completely. The Sagittarius dwarf is being eaten right now. Active consumption. We caught it in the act. The dwarf contains about 400 million stars. Over the next billion years, those stars will scatter across the Milky Way. In 2 billion years, no trace of Sagittarius dwarf will remain except ghosts in the data. But Sagittarius is just the latest victim. The galaxy has fed many times before. Gaia Enceladus was a major meal. About 10 billion years ago, a galaxy 1/4 the Milky Way's mass collided with us. This was not a minor dwarf. This was a substantial galaxy. The collision was violent. Both galaxies suffered, but the Milky Way won. We absorbed Gaia Enceladus completely. The stars now populate our halo. Billions of them, former citizens of a destroyed civilization. The Gaia spacecraft detected this ancient merger by studying star motions. Stars from Gaia Enceladus orbit differently than native Milky Way stars. They move in retrograde directions, tilted orbits, eccentric paths. Their motion betrays their foreign origin. Chemical analysis confirms it. Gaia Enceladus stars have different compositions than native stars. Less heavy elements, different abundance patterns. They formed in a different galaxy with a different chemical history. Now they orbit here, captured, assimilated. The Kraken merger came earlier, 11 billion years ago, an even more massive collision. Kraken might have been half the Milky Way's mass at that time. The merger reshaped our galaxy, triggered intense star formation, built much of our current disk structure. Kraken's remains are harder to identify because they are so thoroughly mixed. But they are there. Billions of stars, the Sequoia dwarf, the Helmi streams, Omega Centauri, a massive globular. Today, the Magellanic Clouds will be eaten. Sagittarius is being digested. Small dwarfs orbit too close. Doomed. In the future, Andromeda will collide with us. That will be the final meal. The merger that transforms us completely. Galactic cannibalism explains why big galaxies keep growing. The rich get richer. Once you are massive enough, your gravity reaches farther. You can capture more victims. Eat them. Grow larger. Your increased size lets you capture even more victims. Positive feedback. Runaway growth. Dwarf galaxies have it rough. They are prey, constantly threatened by larger neighbors. Most of them eventually get eaten. Only a few survive in isolation. The Milky Way dominated the local group by eating everything within reach. We built an empire through consumption. But here is the strange part. Those devoured galaxies are not gone. Their stars still exist, still shine, still orbit. They just orbit us now. The Milky Way is not a single entity. It is a collective, a graveyard empire built from the corpses of dozens of smaller galaxies. You might be made of elements forged in a star that once belonged to Gaia Enceladus. Heavy elements like iron and carbon cycle through the galaxy. Supernova remnants. Stellar winds. Eventually, those elements coalesced into our solar system. Into Earth. Into you. You are partly alien. Made from material that came from conquered galaxies. We are all immigrants. Citizens of an empire that erased borders by eating neighbors. The Milky Way grew big through violence, through mergers, through cannibalism, and we are still eating, still growing, still adding to our collection of stars stolen from others. Scientists hate being wrong, not because of ego, because being wrong means rebuilding everything, recalculating, rewriting papers, admitting uncertainty. The James Webb Space Telescope forced exactly that admission. Webb launched in December 2021, a $6 billion infrared observatory. 100 times more powerful than Hubble, designed to see the earliest galaxies, the first stars, the birth of cosmic structure. Nobody expected it to revolutionize our understanding of the Milky Way. But it did. The breakthrough came from unexpected observations. Webb can see through dust better than any previous telescope. Infrared light penetrates gas and debris that block visible light. This let Webb map regions of the Milky Way we could never clearly see before. The galactic center, thick dust clouds, the far side of the disk. What Webb found shocked everyone. More structure, more stars, more complexity than models predicted. The outer regions of the galaxy were not empty like we thought. Faint stars, populated regions we assumed were void, scattered, isolated. But there, billions of them. Webb also observed satellite galaxies with unprecedented detail. It resolved individual stars in distant dwarfs, measured their ages, their compositions, their distances. Each measurement refined our model of the Milky Way's gravitational field, and each refinement pushed the boundary outward. The critical data came from stellar streams. Webb tracked streams farther than previous surveys. It measured streams at enormous distances from the galactic center. 200,000 light-years out. 250,000. These streams should not exist if the galaxy was as small as we thought. Their presence proved our estimates were wrong. But the real blow came from mass calculations. Webb observed how light from distant galaxies bends around the Milky Way. Gravitational lensing. Einstein's general relativity in action. Measure the bending. Calculate the mass. Webb's precision exceeded previous instruments by orders of magnitude. The result? 4 trillion solar masses. Maybe more. Triple the old estimate. The data was undeniable. Multiple independent methods confirmed it. Scientists could argue with models. They could debate theories. But they could not argue with direct gravitational lensing measurements. Conferences erupted in debate. Some astronomers defended the old measurements. Others accepted the new data immediately. Papers appeared arguing both sides. Slowly, grudgingly, the consensus shifted. The Milky Way is bigger. Much bigger. The textbooks were wrong. Webb continues to refine measurements. Every new observation adds detail. Some measurements push the size even larger. Others suggest we are still underestimating the dark matter halo. The final number keeps climbing. But Webb also raised new questions. If the Milky Way is this big, other galaxies should be too. Webb turned toward Andromeda, toward Triangulum, toward distant galaxies through every subfield of astronomy. This is how science works. New instruments reveal new data. Data contradicts old models. Models get updated or replaced. Nobody enjoys being proven wrong. But the alternative is staying wrong forever. Clinging to outdated ideas because they are comfortable, refusing to accept evidence because it is inconvenient. Webb gave us the evidence, forced the admission, made scientists face the data and acknowledge their mistake. The Milky Way is not the galaxy we thought we knew. It is bigger, heavier, more complex. And we are still discovering just how much bigger it really is. The James Webb Space Telescope changed everything. Not through grand discoveries of distant universe structure, through humble observations of our own cosmic backyard. And in doing so, it revealed how little we truly understood about home. Dark energy is the biggest mystery in cosmology. An invisible force pushing the universe apart, making expansion accelerate, causing space itself to stretch. Scientists discovered it, measured it, named it, but they do not understand it. And bigger galaxies just made the mystery worse. Here is the problem. Dark energy calculations depend on accurate mass measurements. You need to know how much matter exists, where it concentrates, how gravity pulls. Then you subtract all the gravitational attraction from the observed expansion rate. What remains is dark energy, the force accelerating everything apart. But if galaxies are twice as large as measured, they contain much more matter. More matter means more gravity. More gravity means the universe should expand slower, except the expansion rate has not changed. We measured that independently using distant supernovae. The universe is accelerating at a specific rate. That part is solid. So if matter doubled but expansion stayed the same, dark energy must be different than calculated, either stronger or distributed differently, or maybe not uniform across space. The standard model of cosmology assumes dark energy is constant everywhere. Same strength, same properties. The cosmological constant, a fundamental property of space. Bigger galaxies threaten that assumption. If there is more matter pulling inward, you need more dark energy pushing outward to get the observed acceleration. The ratio shifts. The balance changes. Dark energy might be stronger than we think. Or maybe our entire dark energy model is wrong. Alternative theories exist. Modified gravity, variable dark energy density, cosmic inhomogeneities. Each theory tries to explain why the universe behaves the way it does without perfect uniformity. Bigger galaxies give these alternative theories more room to work. Consider the coincidence problem. Dark energy and dark matter contribute roughly similar amounts to the universe's total energy budget. About 70% dark energy, about 25% dark matter, 5% normal matter. Why those specific ratios? Why not 90 to 10 or 50 to 50? The similarity seems suspicious. Double the dark matter by making galaxies bigger, and the coincidence becomes worse. Now you need even more dark energy to maintain the ratio, or you accept that the ratio changed. Either way, the coincidence needs explaining. Some cosmologists suggest the coincidence is not a coincidence. Dark energy and dark matter might be related, different manifestations of the same underlying phenomenon. If galaxies contain more dark matter, maybe they also produce or interact with more dark energy locally in their vicinity. Testing this idea is difficult. Dark energy is invisible, uniform, unchanging as far as we can measure. You cannot point a telescope at it, cannot capture it, cannot study it directly. You can only measure its effects on cosmic expansion. Bigger galaxies also affect baryon acoustic oscillations. These are ripples in the distribution of galaxies across the universe. Frozen sound waves from the early cosmos. Cosmologists use them as standard rulers. Measure the spacing between ripples. Calculate distances. Those distances help measure dark energy. But the ripples depend on galaxy clustering. How many galaxies, how massive they are, how they distribute. If galaxies are bigger and more massive, the clustering changes. The ripples shift. The standard ruler gets tweaked. Distance measurements need recalculation. Dark energy estimates shift accordingly. The Hubble tension gets worse too. This is the disagreement between different methods of measuring the universe's expansion rate. Local measurements using supernovae give one answer. Cosmic microwave works incredibly well. It matches observations across 13 billion years of cosmic history. But it has three parameters: dark matter, dark energy, values we measure but do not truly understand. If those measurements are wrong, the entire model shakes. Bigger galaxies shake the foundation. Not enough to topple it, not yet, but enough to make cosmologists nervous. Enough to question whether our understanding of dark energy is as solid as we thought. The universe is accelerating. That is a fact. But why it accelerates and how much dark energy drives that acceleration just became more uncertain. We measured galaxies wrong, which means we might have measured the universe wrong too. Dark energy remains the deepest mystery in physics. And the mystery just got deeper. 200,000 light-years. That is the current answer. The Milky Way measures approximately 200,000 light-years in diameter, maybe 250,000. The exact number depends on how you define the edge. But this is not the final answer. It is the best answer we have right now. In 10 years, the number will change. Better telescopes, better data, better understanding. The measurement will improve. It always does. Here is what we know with confidence. The galaxy is much larger than 100,000 light-years. That old number is definitely wrong. We have overwhelming evidence from multiple independent methods. Stellar streams, satellite galaxies, dark matter mapping, gravitational lensing. Every technique points to a larger size. 200,000 light-years fits current data. It matches satellite galaxy orbits. It explains stellar stream paths. It aligns with dark matter models. Reasonable, defensible, probably close to correct, but definitely not final. What measurements are we still missing? Many. We need better maps of the dark matter halo. Current models extrapolate from inner regions. They assume certain density profiles, but direct measurements of the outer halo remain sparse. Better gravitational lensing surveys would help. More satellite galaxy discoveries would refine orbits. Improved computer simulations would test theoretical predictions. We need deeper surveys of faint stars. The outer halo contains dim red dwarfs scattered across enormous volumes. Current telescopes detect only the nearest ones. How many more hide beyond detection limits? Are there populations we are completely missing? Future telescopes will push sensitivity deeper. Each improvement reveals more stars. Each discovery extends the boundary outward. We need better distance measurements. Many stellar streams have uncertain distances. Are they 150,000 light-years out or 200,000? The uncertainty makes drawing boundaries difficult. Improved parallax measurements from Gaia will help. But some streams orbit so far out that parallax barely works. We need new techniques. We need to understand galactic winds. Hot gas blows outward from the disk. How far does it reach? Where does it fall back? Is that gas still part of the galaxy? Wind dynamics affect mass estimates. They affect where we draw the line between galaxy and intergalactic space. We need more satellite galaxies. The Milky Way has about 60 known satellites, but simulations predict hundreds. Where are the missing satellites? Are they too faint to detect? Do they orbit so far out we have not surveyed that region? Every new satellite discovery teaches us about the galaxy's gravitational reach. We need to measure the Magellanic Clouds more precisely. Are they gravitationally bound forever or just passing through? Their orbits depend on the Milky Way's total mass. Measure the orbits precisely. Refine the mass. That changes the size estimate. We need to understand where our galaxy ends and Andromeda begins. The dark matter halos might already be touching, but where exactly is the boundary? How do you separate interpenetrating halos? This is not just academic. It determines when the collision truly begins. The Nancy Grace Roman Space Telescope will help. Launching soon, designed to survey huge areas of sky with incredible depth, it will find faint satellites, map distant stellar streams, measure gravitational lensing across wide fields. Each dataset will refine our model of the Milky Way. The extremely large telescope will help too. A ground-based giant with a mirror over 100 feet across, resolving power beyond anything built before. It will observe individual stars in satellite galaxies. Measure their velocities precisely. Each measurement tightens constraints on galactic mass and size. Future surveys will keep improving the number. 200,000 light-years might become 220,000 or 180,000 or 250,000. The uncertainty will shrink. Confidence will increase. But the number will never be perfect. Never final. Just progressively better. Here is what this all means. We live in a galaxy we are still measuring. A structure so large it defies complete observation. We sit inside it, trying to map it, knowing our view is limited. Incomplete, biased by our location. 200,000 light-years is our best answer today. Tomorrow will bring better instruments, better data, better answers. The measurement continues. The galaxy keeps revealing itself. And we keep learning just how enormous our home truly is. The Milky Way is bigger than we thought. Twice as wide. Triple the mass. 400 billion stars. Countless planets. Billions of potential homes for life. And we are just beginning to understand its true scale. This is the galaxy we live in. Enormous. Complex. Still mysterious. Still growing, and still teaching us that we know less than we think. The final number? We do not have it yet, and maybe we never will, but we are getting closer. One measurement at a time, one discovery at a time, one revelation at a time. The Milky Way is 200,000 light-years wide. For now,